Hello, and welcome back to Worked Heat Transfer Examples. Today, we'll be working on an internal convection problem where flow is moving through a channel or a pipe, so the boundary layers between sides of the channel interact with each other. In this problem, air is moving through an 18-meter long rectangular duct with a cross-section that's given at a velocity of 4.5 meters per second. The duct is subjected to uniform radiation heating on the entire surface area at a rate of 400 watts per meter squared. We are asked to find the wall temperature at the exit of the duct. Remember, in a case like this, because we have a constant heat flux, the temperature along the channel is changing. We have a sketch of the problem at the bottom of the page. We know that the inlet temperature is 10 degrees Celsius and the velocity of the fluid in the pipe is moving at 4 meters per second. The length of the pipe is 18 meters. There's a constant heat flux of 400 watts per meter squared. And we are asked to find the temperature on the surface at the outlet of the tube. In this problem, because we're given the cross-section, we can figure out the hydraulic diameter of the pipe. We use this equation, that's 4 times the cross-sectional area divided by the wetted perimeter. That's the perimeter in the tube that the fluid is touching. We know those values, right? So we can get an expression, and we find that the hydraulic diameter in this case is 0.171 meters. Assumptions for this problem include that the pipe has a constant heat flux, that fluid and material properties are constant, that the system is at steady state, and that there are no losses to the surroundings. There may be more assumptions to come in this problem. Again, we'll try to follow our convection flow chart. We want to understand the geometry and boundary conditions, determine relevant properties at appropriate temperatures, use properties to calculate the Reynolds number, choose an appropriate convection correlation, find the heat transfer coefficient, and solve the problem. First, we want to understand the geometry and boundary conditions. Here we have internal flow, we have constant heat flux, and we have a rectangular pipe, or at least not a circular pipe. We know that we need to find the entrance lengths in the pipe. We want to determine whether the flow is laminar or turbulent, because that will change the length of the entry region. We'll also want to use a Nusselt number correlation, one of the correlations listed here, but we'll need to know if the flow is laminar or turbulent before we do this. Now we want to determine relevant properties at an appropriate temperature. For internal convection, the temperature we're interested in is the average temperature between the inlet and outlet temperatures. You may notice that we don't know the outlet temperature yet. So we'll see if we can get the right temperature for properties. We know the inlet temperature, we don't know the outlet temperature. So if we do a first law analysis on the pipe, we know that all the heat that goes into the fluid is coming from that heat flux on the edge of the pipe. We know that that is equal to the mass flow rate times the specific heat times the change in temperature in the fluid. Now here, because I'm heating the fluid up, I know that the outlet temperature is larger than the inlet temperature, so I've written my delta T as T out minus T in. Unfortunately, we don't know the specific heat, and we don't know the outlet temperature. In order to find specific heat, we need some average temperature, the average temperature between the inlet and the outlet of the pipe. So because we don't have this yet, we'll make an assumption, and that'll help us find the specific heat, and then we'll have to check that assumption later. So I have a table for gases at atmospheric pressure, I'm going to assume that the average temperature is 300 degrees Kelvin. So I'll read my temperatures off this line in table A.4. I find that the density is 1.16 kilograms per meter cubed. I know the viscosity. I know the thermal conductivity. I can find the Prandtl number on the table, and I can get the specific heat. Now, once I know the specific heat, or an assumption for the specific heat, I can go back to the equation that I had, the first law analysis on the flow, on the fluid moving through the pipe. I can rearrange my equation to get an equation for the temperature at the outlet of the pipe. And then I can use that to find the outlet temperature. I put some numbers into my calculator. I simplify the equation a little bit, and I find that the outlet temperature, with the assumption that the average temperature is 300 degrees, was 42 degrees. Now I can also find that average temperature because I know the inlet temperature and I assumed the average temperature. And if I do that, I found through my assumption that my average, or that my outlet temperature was 44 degrees Celsius, which is pretty close to 42. So I'm not going to iterate. If my values here were very far apart, then I would maybe update my guess and redo this part of the calculation until I got something that converged. Now that I know my properties of the fluid, I can calculate the Reynolds number. The Reynolds number here, now remember we have to use the hydraulic diameter because this is a rectangular cross-section, is equal to the velocity of the flow moving through the pipe times the hydraulic diameter divided by the viscosity. I know all this information, so I can plug it into my equation, and I see that the Reynolds number is over 48,000. That's bigger than 2,300, which means that the flow is turbulent. Now I have to see whether or not it's fully developed. For turbulent flow, both the hydrodynamic and thermal boundary layers become fully developed at approximately 10 diameters into the tube. In this case, that's 1.71 meters. So both boundary layers are fully developed for most of the length of the tube. Now it's time for us to choose an appropriate convection correlation. I have 4 choices, and because I found that the flow is turbulent, I can automatically eliminate 2 of them. I'm going to further assume that the rectangular duct we're talking about is smooth. So I'm going to get rid of my rough and transitional Nusselt number correlation. And then because I'm heating the fluid, or that the surface temperature of the channel is larger than the temperature of the medium or the fluid running through the channel, I choose N equal to 0.4. Now I have the Nusselt number correlation I'll use for this problem. Finally, I'm going to find H and solve the problem. So I have my Nusselt number correlation. I know Reynolds number and Prandtl number, and I can use that to find a Nusselt number. In this case, 112. I can use the definition of the Nusselt number to find the heat transfer coefficient. Remembering again that this D should be the hydraulic diameter of the duct. Again, I put numbers into my calculator and I find that the heat transfer coefficient is 17.2 watts per meter squared Kelvin. Now I have to try to use this to find the temperature of the surface at the exit of the pipe. So at a distance of x is equal to L, I know that the heat flux that's coming off the surface at that point goes into the fluid that's moving through the channel. So I know locally that Q double prime is equal to H times delta T. In this equation, I know T out, I know H, and I know Q double prime. So I can get an expression for the temperature of the surface at the end of the pipe. I put some numbers into my calculator, and I find that the surface temperature at the edge of the pipe is equal to 65.3 degrees Celsius. We're finished another worked heat transfer example, and hopefully you feel like now you have knowledge of the transfer of heat. Thanks, and I'll see you next time.